Today, we are going to embark on a really fascinating journey. We're moving from the sort of mechanical, rigid models of the past over to the optimizing, highly human-centric models that literally drive modern central banks today. So if you've ever wondered how economists actually, calculate the future of our economy, well, you are absolutely in the right place. Let's get started. Okay, let's just do a quick rundown of our syllabus for today. We're going to start with the flaw in the SOLOW model, then introduce the Ramsey household, unpack the Euler equation, explore the transversality condition, and finally, wrap up with how we actually solve the modern model today. All right, section 1, the flaw in SOLOW. So, I want you to think back to our previous lesson on Robert Solow's celebrated 1956 economic growth model. Now, look, it was absolutely brilliant for its time. It gave us a phenomenal way to look at long-run capital accumulation. But it had a pretty fatal flaw. It basically treated humans like robots. I mean, in Solow's world, households just blindly saved the exact same constant fraction of their income year after year. It completely ignored incentives. It literally didn't matter if interest rates were soaring through the roof or plummeting to zero, or, what households expected about the future. That savings rate, it never budged. So, class, I really want you to ponder this stark question. Where does that savings rate actually come from? Because figuring that out, solving that specific puzzle, it changed the entire trajectory of dynamic macroeconomics. We can't just pull a savings rate out of thin air if we want to truly understand how a real economy reacts to policy changes, right? Which brings us to section 2. Enter the Ramsey household. To answer that question of where savings come from, we have to look at the groundbreaking work of Frank Ramsey, David Cass, and Tallene Koopmans. And comparing their frameworks illustrates just a massive paradigm shift. We moved from a SOLOW world, fixed assumptions, no real human preferences, to a Ramsey world. In this new world, we have a forward-looking, highly rational household that is continuously weighing consumption today against consumption tomorrow. The savings rate is no longer just some fixed static number. It's a dynamic choice, and it's made to maximize lifetime utility. To kind of ground all this abstract math, I want you to picture Robinson Crusoe marooned on a desert island, okay? He has a pile of potatoes. Every single day, Crusoe faces a really tough choice. How many potatoes should he eat today to satisfy his current hunger, and how many should he plant in the ground to ensure he actually has a crop next season? He is constantly optimizing his potato crop to make sure he survives and thrives over his entire lifetime. And that, in a nutshell, is the essence of the Ramsey household. So the absolutely crucial point here is figuring out the exact mathematical toolkit our household uses to make this continuous, lifelong choice. I mean, how do we actually put Crusoe's dilemma into a workable equation? Let's get into the math. Section 3, Unpacking the Euler equation. Pay really close attention to this concept, class, because I'm telling you, it is the beating heart of modern dynamic optimization. Meet the Euler equation. Now, this isn't just some dry mathematical formula to memorize. It's practically the golden rule for trading the present for the future. It directly links the growth rate of consumption to the interest rate, to our rate of time preference, and to our risk aversion. Let's break down the intertemporal forces at play here. The Euler equation weighs the marginal product of capital, which is basically just the reward you get for saving, against the household's natural impatience, or what we call the rate of time preference. Let's go back to our island for a second. If the soil yields a massive potato crop next year, meaning you have a high return on capital, well, you'll happily go a bit hungry today to plant more, right? But if the yield is terrible, you might as well just eat your potatoes right now. The Euler equation mathematically captures this exact balancing act. Okay, so the Euler equation tells us the optimal path step by step, but we still have an infinite horizon to deal with here. If the household lives forever, or maybe plans for a dynasty that lives forever, what's to stop them from just borrowing infinitely to fund a massive consumption binge today? This brings us to a major boundary issue, which leads us to Section 4, the transversality condition. To make sure our mathematical model doesn't allow for completely irrational, crazy endgame behavior, we bring in the transversality condition. We basically need this rule to cap the infinite timeline. In plain English, this rule means you can't die with a massive explosive pile of debt, nor should you die with a huge pile of unconsumed resources. Why? Well, think about it. If you died with a mountain of leftover resources, that would mean you failed to optimize your utility while you were alive. You could have eaten more potatoes. So transversality really matters because it acts as the ultimate reality check on that infinite horizon. It forces the household to eventually settle its accounts. It completely prevents these infinite Ponzi schemes where you just roll over debt forever. And it ensures that our economic models don't just spiral off into mathematical impossibilities. Now, notice the turnpike dynamics mapped out for an economy that ends at a specific time. Let's call it time t. A completely rational household will keep capital pretty steady for most of the timeline, but then they sharply run down all their capital to zero right at the very end. They literally consume it all to maximize their final consumption, which perfectly satisfies the transversality condition. Pretty cool, right? So, now that we understand the beautiful theory behind the Ramsey household, the Euler equation, and the transversality condition, we kind of have to confront the ugly reality of actually calculating these answers, because doing this math by hand for a massive, complex, real-world economy, yeah, it's practically impossible. Let's dive into Section 5, Solving the Modern Model. Let's see how all this theoretical stuff builds the very models actively used by central banks all around the world today. Look, the abstract math we just learned isn't just some academic exercise designed to torture graduate students. It is the exact operational language of modern forecasting. Dynamic stochastic general equilibrium, or DSGE models, which are used by the Fed, the ECB, the IMF, they all have a Ramsey household right at their core. When the Fed staff evaluates the welfare cost of inflation or some new tax reform, they are calculating it based on these perfectly optimizing households. But here's the catch. To make these models realistic, we can't just have one single Robinson Crusoe, right? We need to add heterogeneous agents. We need rich people, poor people, different income shocks. And the second we add these realistic dimensions, we slam into an incredibly painful mathematical roadblock. It's known as the curse of dimensionality. Computing the optimal path across all these different variables causes the possibilities to just explode exponentially. And when we look at the complexity of this, adding just a few more state variables to our simulated economy pushes our computer algorithms straight into the red, horrible zone of operations. Standard approximation methods completely fail here. The analytic solutions simply take way too long, or they just devour too much computer memory. So, to tame this beast, modern economists have basically had to become computer scientists. They're abandoning a lot of traditional methods and utilizing continuous time stochastic calculus, using tools like Ito's lemma to replace clunky grid integrals with smooth derivatives. And more recently, they are even using deep learning and neural networks. Because neural nets are compositional rather than additive, they can actually process these massive simulated data grids and break the curse of dimensionality. This finally lets us find the optimizing paths our Ramsey households take. Well, I leave you with this final thought, class. We've seen how macroeconomics evolved from Solow's mechanical robots to Ramsey's optimizing, forward-looking households. And honestly, it's a mathematically stunning achievement. But the next time the Fed changes interest rates to influence the economy, I want you to ask yourself,
Are you perfectly adjusting your Euler equation to maximize your lifetime utility, or are these highly advanced models maybe still missing a crucial piece of the human puzzle? Thank you for joining today's explainer.